Okay, thanks, Bjorn. So, hi everyone. Thanks for being here, the after lunch session. I'm Aakar, and I'm from the DGP lab at University of Toronto. And today I'll talk about the generation and perception of squeezing sensations on the wrist. I did this work in collaboration with my amazing co-authors, Antony and Ravin. Okay, so this is a cross-section of our skin tissue, and this shows that we have a number of different tactile receptors on the skin that result in our perception of different kinds of stimuli, touch, vibration, pressure, temperature, pain, and itch. And most of our work in computationally generating and controlling tactile stimuli has been on vibrations or to some extent force feedback, point-based pressure, right? The other stimuli are rarely investigated. And so in this work, we investigate a specific type of pressure stimulus, which is squeezing around the wrist. So let me first show you our device, which we call HapticClench, which generates squeezing sensations on the wrist. So focus on the spring area. So you might have seen the spring contracting on the wrist. I'll play it again. Okay, so that's essentially the whole system, right? So you can imagine this being integrated into smartwatches, fitness bands, armbands, or even smart clothing. Now, HapticClench uses springs made out of shape memory alloys, or SMAs, that contract when current is passed through them, right? They're very popular in certain use cases. And these shape memory alloys relax back when the current that is being given is stopped. So why do we use shape memory alloys? Are there other existing methods for generating these type of squeezing sensations? Now, so far, the only major investigations that have been done in this space use pneumatic actuation, which uses air pressure similar to a blood pressure cuff. Now, if you've ever experienced a blood pressure monitor, you know that it feels like it's compressing your skin from all directions. And that is because as the cuff inflates, it applies forces that are tangential to the surface of your skin. Now, if you look at the squeezing sensation that's generated from a contracting wire or spring, it results in tangential forces, but it also results in shear forces that are parallel to the contraction. And so squeezing from wire contraction is slightly different compared to the compression that you get from pneumatic actuation. Now, the problem with pneumatic actuation is that it requires this bulky setup with the cuff and the air valve. And so this is not exactly something you can integrate into a thin wearable device or clothing material. Plus, because it requires so much area, we cannot generate sensations that are very precisely localized. And finally, the high inflation and deflation time for the air is also a major drawback. For HapticClench, as you can see, the whole setup is significantly less bulky. It has an SMA spring, a rubber polyester band, the white band that you see, and a microcontroller, right? And in arriving at this final prototype, which seems very simple, but we went through a pretty long design process, and our primary goal here was to generate strong squeezing sensations, right? And the strength of these sensations is expressed in terms of the load of the force exerted by the spring. But the strength is not the only property that we are interested in. So we define 3 properties of squeezing feedback that tell us about the squeezing competence of a particular device, right? These are the span, the load capacity, and the load throughput. Now, span is the width of the actuating wire or spring on the skin. So as the span becomes higher, we need a higher load to generate the same amount of pressure on the user's skin, because pressure is inversely proportional to the area, right? And so ideally, we want a device with a lower span. Plus, the lower span also means that we can generate precisely localized sensations. Load capacity is the maximum load a squeezing device can generate. And so this informs us about the limit of the squeezing strength of the device, and we want it to be as high as possible. And finally, load throughput is the maximum load a squeezing device can generate in 1 second, which essentially informs us about the speed of actuation. And again, we want this to be as high as possible to reduce the latency. And so overall, what we need from a squeezing feedback device is lower span, higher load capacity, higher load throughput. And this figure shows our prototypes at various stages of the design. And there were multiple factors here, but I'll just talk about one, which is the switch from a wire in the beginning to a spring at the end. Now, we need the load capacity of the device to be consistent from one actuation to the other, right? And so that means that when the wire relaxes in the absence of current, it should restore back to its original length. The problem is that SMA wires need an external pull force to restore back to their original length. Whereas with springs, the outward force provided by the squeezed skin itself is enough for the restoration. So the spring also provides a higher load capacity, and therefore we switched from a wire to the spring, even though the spring has a lower span. So in the final prototype, the span is 3.45 millimeters, load capacity is 1.63 kgs, and the load throughput is 1.63 kgs in 1 second, which means that the spring can reach the maximum load within 1 second. And if you think about it, 1.63 kgs in 1 second is pretty good, given the lightweight setup that we have. But there is a caveat here, which is that the power required by the spring to generate this maximum load capacity is high. So this curve shows the load generated by the spring when a particular amount of power is applied for a time of 2 seconds. And for the maximum load of 1.63 kgs, you can see that we need about 32 watts. Now, of course, the user's detection threshold, which is the lowest load at which they start perceiving the squeezing sensations on their wrist, should be much lower than 1.63 kgs. And therefore, we wanted to know what that threshold value is. And so we conducted an absolute detection threshold study with a 2-down, 1-up staircase design, the standard design, where participants had to respond if they felt a stimulus. I'll skip the procedural details, which are in the paper. So the results showed that the absolute detection threshold stands at 0.16 kgs. You can see it's depicted by the red dotted line. And this 0.16 kgs requires a power of 5 watts, which is still slightly high, but manageable for wearable devices. Now the thing is that here the users were only focusing on the detection when they were doing the experiment. But what happens if the user is distracted? And so we conducted an absolute detection threshold study where the user's primary task was to play a game on a desktop, and they had to do the study. And so with the distracted absolute detection threshold, we found that the value was almost the same as the previous one at 0.17 kgs, right? So now the thing is that we might see a difference here if we study more cognitively demanding primary tasks. But for now, this is what we found, which is that the users can recognize squeezing sensations even when they're distracted at the same threshold, essentially. Okay, so as we saw in the graph, we can modulate the power to control the load. And so let me just show you how a force sensor's value change when we have a weak sensation versus when we have a strong sensation. So this is the weak squeezing sensation, and then we have a stronger one, which goes up to a very high value within almost the same amount of time. So now the question is, how many levels of these squeezing loads can the user actually distinguish? And so we conducted a JND, a just noticeable difference experiment. And again, without going into the details, the results showed that the users were able to distinguish between 4 different levels of the squeezing loads. Okay, so squeezing with a single spring works quite well. And so the next thing we explored was whether we can actually take advantage of the small span and use multiple springs to convey different spatial squeezing patterns. And so here we have 3 springs, 1, 2, 3 in parallel. And we conducted an experiment to see whether users can distinguish between 15 different spatial patterns, which you see here. So there are 3 single patterns, 6 double patterns, 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 3, 2, and 6 triple patterns. So for example, with 1, 3, 2, the springs 1, 3, and 2 actuated one after the other, and the total duration of the pattern was 3 seconds. And we played these in a random order, and for each, the participants had to select the one they perceived, that they thought they perceived, out of the 15 possible patterns. And the results showed an overall recognition accuracy of 85%. Now, if we only looked at the accuracy of these 10 highlighted patterns, it's almost 92%. And for the other 5, it's just 72%, which is a big difference. So what's happening here? Now, if you see, most of the confusion was within the double patterns. So the problem was that the participants could tell the relative positions of the sensations, but not necessarily their absolute positions. So for example, if 3-2-1 was played, they knew it was one after the other. But if 3-1 was played, they got confused whether it was 3-1 or 3-2. And so spatial squeezing patterns should be designed with respect to relative positioning and not absolute positioning. Okay, so let's move to the next question that we ask, which is gradual squeezing. Now, if you think about squeezing, it doesn't have to be a sudden, instant experience, right? In fact, as opposed to vibrations, which can get annoying with longer durations, squeezing feedback for ambient information for longer durations might be better. So, for example, you can track the progress of a microwave. You know, the load increases as the timer counts down. And you can imagine this for any other type of information that varies with time. Now, the question is, can the user actually feel the squeezing sensation increase if the increment is so gradual? And past work on vibrations has shown that the longer the vibrations continue, the intensity of the vibration that the user perceives becomes less and less. So is that the case here as well? And therefore, we conduct another experiment where we compare two types of increment. One was a continuous increase from a low load to a high load over a period of 1 minute, and the other was a staggered increase where we doubled the load every 15 seconds. And for the baseline, we had a third pattern, which was simply holding a constant load. And the participants were asked to play an obstacle game as their primary task, and one of these 3 patterns was played at any random point during the game. And after the pattern was complete, the participant was prompted on whether they felt an increase in squeezing sensation or just a constant squeezing. And this is the result. The users recognized the continuous pattern as an increase only 65% of the time, while it was 90% for the staggered one. So it's pretty clear that staggered increment is better for conveying gradual increase in squeezing strength. Now, this is only one basic aspect of using ambient squeezing sensations, and we need a dedicated investigation in this space to know more about how ambient squeezing sensations can be designed. So, for example, we only studied duration of 1 minute, and maybe we want these results won't replicate themselves for, let's say, 10 minutes. Now, apart from squeezing on the wrist, we also experimented with other form factors like squeezing on a finger for a ring, and loose squeezing textile bracelets, which have this additional visual component. So we essentially have a stronger wire sewed into the bracelet, and the user can simply pull it to restore it back. And so this provides a combination of visual and haptic feedback, which could be useful for providing notifications that are meaningful to the entire group or to the social space that the user is in. And this could possibly be an interesting thread for future exploration. Okay, so we are almost at the end. Let me summarize the guidelines for using shape memory alloys for generating squeezing sensations. First, SMA springs are more preferred than SMA wires because they do not require external restoration, and the force from the squeezed skin is enough to restore them. SMA springs also have a higher load capacity than SMA wires. SMAs follow a non-linear power load curve, which should be derived in advance to facilitate design for a particular wire or spring type. The curve is subject to fluctuations based on ambient temperature, overheating, or physically overextending the spring. Now, the details for these, I haven't really gone into them, but they're in the paper. Now, the problem is that because of these fluctuations, SMAs have significant limitations with respect to whether they can be applied to the real world right now, right? And for example, higher loads require higher power. We already know that. And they also lead to higher temperatures of the wire, right? So the wire gets heated up. And there is ongoing work on these alloys that minimizes these issues. In fact, some of them are available already, but only for industrial orders. So some alloys claim to solve these problems to a certain extent, but they're not available freely, and they're only available if you make a big 10,000 unit order. Now, a related issue is that a higher temperature means that the spring will take longer to cool down, like up to 10 to 20 seconds. So even though the spring relaxes to its original length instantly, the cooling time means that we cannot actuate it again immediately. But we can solve this problem by having multiple springs and actuating them in an alternative fashion so that the user feels like they're getting actuated again and again, but we're actually using 2 or 3 springs. Now, finally, we also need to design the device such that it's immune to changes in ambient temperatures, perhaps by using a feedback loop. Okay, so we've talked about the guidelines for shape memory actuators. I'll now summarize the guidelines for the design of squeezing sensations, regardless of whether we use shape memory actuators for the actuation or not. So first is that the detection and J&D thresholds from our studies should hold for wrist squeezing sensations with similar spans, even if they are generated using other wires or motor-based mechanisms. Secondly, span, load capacity, and throughput should be used as metrics to compare different devices. So for example, if somebody develops a new device for squeezing sensations, they can compare these 3 properties with our device and know instantly which one seems to perform better. Thirdly, spatial squeezing patterns should be designed such that they rely on relative positioning instead of absolute. And finally, for gradually increasing pulses, a staggered increase in load is more effective than a continuous increase. And the step increases should be exponential in accordance with the values that you've got in the J&D. Finally, apart from the usual notifications and patterns, we think that squeezing sensations can be useful for other applications, which are very different from what we are typically used to with vibrations. So for example, ambient awareness, again, vibrations cannot be used for longer durations, but squeezing sensations probably can be, and we have touched upon that a bit. Squeezing sensations might prove to be very useful for effective communication, for communicating emotions. And finally, the question is, can we replicate human squeezing? So for example, can a person remotely convey a squeezing sensation to their friend or a significant other in a way that seems realistic, not just in terms of the intensity and the duration, but also in terms of the actual feel of that sensation? And with that, I'll end. I'm open to questions.
A microphone here in the middle of the room for questions. Please state your name and affiliation before your question. And since the Q&A period is pretty short, I would suggest that subsequent authors start preparing during the Q&A.
Taeyeon Lee from KAIST. I had an interesting talk, and I can imagine some interesting applications for the squeezing sensation. The squeezing sensation might be affected by the size of the length of SMA and the size of the wrist and the state of the muscle, like relaxed or constrict. How did you control that kind of factors in your experiment?
I'm not sure if I understand the question completely. So the factors are the length of the wire,
and the size of the wrist, and the status of the muscles on the wrist.
Okay, yeah. So we actually, in our detection threshold studies, we recorded the participants' wrist circumference and the wrist's top skin fold thickness. So essentially, the thickness that you get when you do something like this, which is, and we did not see any correlations whatsoever for both properties. So the wrist circumference and the skin fold thickness did not affect the detection thresholds. One factor that we think might affect this is age, because our users were pretty young, like 20 to 35, and I think that might be because as you age, your sort of tactile perception goes lower and lower, according to some psychophysical studies. With respect to length, yes, the longer the length of the wire or the spring, the contraction, the load capacity increases. So yeah, we had a fixed length essentially for all users.
Okay,
and that's
thanks.
another factor that the
Thank
designer
you.
has to keep in mind.
Thank you.
Yeah.
Hi, Sean Fulmer, Stanford University. Nice talk. I'm wondering if you could talk a little bit about spatial acuity and if you did any studies of that. It seems like the study you presented about the spatial patterns has a lot to do with our limits in tactile spatial acuity, which in the wrist area I think is kind of on the centimeter scale. So I'm wondering if you could talk a little bit about if you've done any testing about spreading them out more. Yeah.
Okay. So with respect to spatial acuity, I mean, so for example, in our patterns that we did, we also had single wire patterns, right? So we had patterns where just the one of the wires was actuated. And even there, we saw that the users were able to distinguish the first wire and the third wire, right? So they knew, okay, this is the first wire and this is the third wire. But when it came to the second one, they were always confused whether it's the left one, the right one, or the middle one, right?
I guess that might suggest that might be something you want to look into in future work is about that spatial acuity. So thanks.
Yeah.
Thank you. Let's thank our speaker again.